So far we covered the topics which are covered in first unit is general considerations in machine design and design process, engineering materials, properties and selection, manufacturing considerations in machine design, BAS course completed, refer numbers completed. Today we'll actually the simple stress topics already covered in last class, but previous classes. But let me recollect once again because many of the students are attended the PPT classes at the time. Okay, so this is one of the important topic that is required to design something. So in a simple stresses, you're going to discuss axial stresses, bending stresses, and torsional stresses. Okay, let's move to the stresses. Some of your friends already told that, or you know very well, the stress is nothing but resistance offered by the body per unit area is nothing but stress. So in other words, whenever there is an external force, obviously there will be an internal resistance about against the external force. Then whatever the internal resistance offered by that body due to that external force is called the what you call strength of the material. Strength of the material. So internal resistance offered by the body against external load is nothing but stress or strength. So to design something, the induced stresses are very important. Here you will find this in a simple stresses topic. We're going to discuss about the axial stress, bending stress, and shear stress. What is axial stress means when the load is applied axially. Like in this case, the load is applied along the axis. Here you'll find this is actually axis of the member. Whenever the load is applied along the axis, that is called the axially loaded member. And the stresses which are induced in this axially loaded member is called axial stresses. The stresses which are induced in the axially loaded member is called axial stresses. And in axial stresses or axial loads, we have two types of axial loads. When the load means when the low force direction is away from its center, then it is called a tensile load. And you know that for a force is a vector quantity, force is a vector quantity. It has the magnitude will be there, and at the same time for this magnitude there will be a direction. Either the force is acting left to right, right to left, top to bottom, or upward direction, topward direction. Like that, it has certain direction. And at the same time, the force is also having one of the force characteristics is line of action, where it is acting. Whether it is acting the radially, perpendicular force, or whether it is acting axially. That is also one of the important aspect. Okay, so in this case, in axial loaded condition, the load is which is acting along the axis. Load is acting along the axis, and here the load is a tensile nature load. The load direction is away from its center. Away from its center. That's what it is called a tensile load. If the load direction is towards its center, then obviously it is called a compressive load. When load direction instead of outward direction, if the load is inward direction like this, then this is called a compressive load. And the stresses which are induced in the compressive load is called compressive stresses. Compressive stresses. So in axial condition, there are two stresses. One is an tensile stresses, another one is compressive stresses in axial load condition. So in this example, there is a pull load of P quantity which is acting one end of the what you call cantilever rod. That is, a rod is supported at this end, and other end there will be a load of a P quantity, and the cross section of this rod is a circular cross section of diameter D. Then length of the rod is L. Then this rod is subjected to a sort of elongation when the load is applied. the length is elongated. When the rod length is elongated, obviously the diameter of the rod is decreases like this. Due to application of P, whatever the L length rod will be, the length is increases. When the length is increases, that is called the what you call longitudinal strain, and the diameter increasing concept is called a lateral strain. Diameter decreasing concept is called a lateral strain. So your rod is subjected to sort of longitudinal and lateral strains. Okay. So here the stress induced in a normal direction. Here instead of the stresses are more in normal direction compared to the lateral direction. So the stresses are maximum in normal direction. That's why we would like to calculate a stress in a normal direction. Then the normal stresses on this cross section, the normal stress induced on this cross section is a load divided by its cross sectional area. Load divided by its cross sectional area. It is a circular member. The cross section is a circular member. Then obviously area is pi by 4 d square is the area for a circular member, and the load is here applied. P quantity is a load applied. So the stress which are induced normal to the cross section is sigma. Especially in this case, those are the nature of the load is tension. That's why it is called tensile stresses. So tensile stresses are P by pi by 4 d square. General units are either in Newton meter square or Newton per meter square or Newton per mm square is a common units for stresses. Okay, so this is the stress which is induced in axially loaded member. Even if it is a compressive load also, the quantity is same, but the direction is negative. That's it. Even though it's a compressive load. The same example, if the rod is in a compression subjected to compressive load like this, in that case also the stress value is same because the load value is same. In that case also the stress value is same because load is if at all load is same, then cross sectional area is same, then obviously the stress induced in a compressive nature is equal to load by cross sectional area. That's why it is same of your value. Okay, and if you look at how the stress distribution will be means it is an uniform nature of stress distribution you may observe here. If you rewrite the thing, then this is equal to sigma t is equal to 4p divided by pi d square. 4p divided by pi d square. Here the p is constant for this problem, that is the load is constant because we are discussing the static loads. Load is constant, load value is constant. Then only the variable is d here, diameter. Only variable is the other p is constant, other variable is d. For this problem, d is also constant. Then the stress distribution of this circular cross section, if you plot the stress distribution, it is a constant stresses of a quantity sigma t, or we can say uniform stress distribution over its cross section. And obviously for every stress member there is a neutral axis, but for a tensile stress cases or for compressive stress cases or the load is axially load cases, neutral axis is neglected, not required here. But for this is a geometry symmetric about central axis, then neutral axis is its geometric center only. The member is symmetric about central axis, then neutral axis is a geometric center only. Okay, this is about the axial loads and axial loaded member. And if at all the member is subjected to the perpendicular load like this, if the load direction is perpendicular to the axis or radial direction, then there is a possibility here that due to this radial load, your member may be bent like this. The beam may be bent like this. Due to this, you may find the deflection maximum at its extreme end. You may find this the deflection maximum at extreme end, and whatever the fixed location, there you'll find the maximum stresses. At the location A and B, you'll find the maximum stresses. This is already studied in your bending moment, bending stress concept in your strength of materials. Okay. And you know that these stresses are called, what are the stresses which are produced due to the bending moment? These stresses are called flexural stresses. Why it is flexural stresses means the stress quantity is varying. One direction it is a tensile, another direction is a compressive. Just if you observe the stress distribution plot over its cross-sectional area, if you take the cross-sectional area of the member, then you may find stress distribution is like this. If you take the neutral axis, above the neutral axis, the load based on the load direction, above the neutral axis, the member is bent like this due to the application of the what we call load. Sorry. Due to application of the load, your beam is bending like this. So whatever the layers on the top side of your neutral axis, if you try to plot the neutral axis, what are the layers on top side of the neutral axis subjected to tensile load, and bottom side of the neutral axis are subjected to compressive load. So then if you observe the load distribution, load distribution is like this. Here at top side, at extreme fiber, the load is maximum tension, and at the neutral axis, the load is the stress is zero at the neutral axis. And other direction, the stress value is increases and reaches to the maximum at its extreme end. This is the stress distribution of the bending stress distribution uh, over its cross section. So the stress values are varying along its cross section. That's why these stresses are called flexural stresses. Flexural stresses. And to calculate this bending value of bending stresses, first thing you have to know the concept of bending moment. So bending moment is nothing but force into perpendicular distance. Force into perpendicular distance. Here we have only one point load. So P is a load at extreme end. The length of distance is L, so that the bending moment maximum is at its XX cross section, where this XX means at this one at AB. AB is will produce it is produce a maximum bending moment. So maximum bending moment is equal to P into L, so many Newton meters. Once if you know the bending moment from your known relation, that's a bending equation, E by R is equal to M by A, that is equal to sigma by Y. From this you may write the bending stresses. This is actually the bending equation. You already derived the bending equation in your strength of materials. So E by R is equal to M by I, that is equal to sigma by Y. So from this, you may calculate the bending stresses from the first two terms or last two terms. But here it is very easy to calculate bending stresses from the first two terms, because you know the bending moment. So bending stresses sigma by Y is equal to M by I into Y, where sigma is a bending stresses, Y is the distance from the neutral axis to the outermost fiber, and M is a bending moment, and I is a moment of inertia. Then bending stress is equal to M by Y into I, M by Y into I. Sorry, M into Y divided by I is a bending stresses. So that is equal to so many Newton per meter square. Like this, we can find out the bending stresses. Okay. So if you substitute the values, bending moment is equal to P into L, and where you get the maximum bending stresses, and then if you draw the cross section of the member, at the neutral axis, the bending stresses are zero, or the stresses are zero at neutral axis. Neutral axis will be, this is the symmetric section, then the geometry axis is the neutral axis, or central level axis is the neutral axis. Then the bending stresses from this point to at the what you call the uh, A layer, that is outermost layer, it is maximum, that is its value is d by 2. Its value is d by 2, because total diameter is d, then it obviously it will be d by 2. And those are other maximum, other direction, here also the value is maximum. Then bending stresses at point A, that is A location is m by m into ya divided by bending moment of inertia at neutral axis, but moment of inertia at neutral axis. So in this case, the moment of inertia is constant for a section. Moment of inertia is constant for a cross section. If it is a circular cross section, the moment of inertia is pi by 4. Pi by 64 d power 4 is a moment of inertia. If it is rectangular cross section, then it will depends upon a thickness and weight. BD cube by 12 is a moment of inertia. Okay, but in this case, the bending moment is constant and the moment of inertia is constant for the section. Then only variable is the YA, that is whether you'd like to calculate the stresses at this location or at this location. So where we'd like to calculate the stresses, based on that the YA values depend. If you want to calculate at A, YA value is the d by 2. If you want to calculate the stresses at somewhere else at middle, then YA value is varying. That is the value, this much is the YA value. That means the stresses are directly proportional to the what you call distance between the neutral axis and the layer where we'd like to calculate the stresses. The stress value is proportional to y. That's what it is, proportional to y. Then y is closer to neutral axis, the stress is minimum. If the y is farther to the neutral axis, the stress is maximum. That's why the stress front is distributed like this. If y value is at the neutral axis, the stress value is 0. Y is at somewhere else at middle, we have a certain stress value. And at y is equal to ya, the stress value is maximum. Okay. Similarly, like the other direction also. This is the bending stress and bending stress distribution. Similarly, if at all, if a member is subjected to a twisting moment, if a member is subjected to a twisting moment, then there is a due to this twisting moment, the torque or twisting moment, you may find the stresses which are generated in this member is uh, torsional stresses. Torsional stresses. It's also called torsional shear stresses. So, in this example, the rod is a cross-sectional one. D is the diameter of the rod, and L is the length of the rod, and it is subjected to a twisting moment T. Subjected to a twisting moment T, and that is subjected to at a distance of some distance from its what you called neutral axis, or you can say the geometric axis. Okay. So for that, the torsional stresses can be calculated from the torsion equation. T by J is equal to tau by R, that is equal to G theta by L. And this is the torsion equation. And from this, we can calculate from first two relations or second two, first and second or first and third. You may use any one of them. But here the twisting moment is given. That's why it is better to calculate the first relation. Here the T is a twisting moment. J is a polar moment of inertia, tau is a torsional shear stresses, and R is a radius where we'd like to calculate the stresses, or it's also called radius of curvature. Okay, so then from first two ones, so T by J is equal to tau by R, then tau maximum is equal to TR by J, TR by J. So this is the torsional shear stress of a member. And here G and theta L. G is a rigidity modulus, theta is a torsional twist, and L is the length of the member. And for a calculation of this, what you call the twisting moment, here also we use force into perpendicular distance concept, like your bending concept. So here for a cross-sectional member, if the tangential load is acting on the top side, then the twisting moment is created is equal to tangential force P multiplied by eccentric distance. Eccentric distance. Here the eccentric distance is d by 2. Then if we substitute the values, then here twisting moment and J. Twisting moment is constant for a problem. J is also constant for the cross section. Then the torsional shear stress is directly proportional to the radius of the member. Radius of the member. If you take the radius of the member, if this is the maximum radius of your component, that is this one, maximum radius r maximum. If r is equal to 0, somewhere else here at the neutral, the vertical geometrical central axis, if r is equal to 0, then substitute 0 here. The stress is directly proportional to 0, means stress is equal to 0. If r is equal to 0, the stress value is 0. That side is 0 here. If r is equal to r maximum, that is at this location, the stress value is maximum. Like that, the stress is increased here. Okay, it is reaches to maximum at this location. Okay. Similarly, this in other direction, in other side also the stress value is at the outermost fiber, the stress value is maximum. That is, the shear stress is maximum on the surface of the members. Surface of the members, it is a minimum at its geometrical axis. It is a minimum at its geometrical axis. Okay, then shear stress is directly calculated by this by substituting this what you call the bending moment, sorry, twisting moment. Substituting a twisting moment, force into eccentric distance. This is actually the T value multiplied by the R divided by J. You'll get the what you call torsional shear stresses. And you know that for a circular members, the J value is pi by 32 d power 4. Polar moment of inertia is pi by 32 d power 4. You know that polar moment of inertia, we can say it is equal to moment of inertia about the x-axis plus moment of inertia about the y-axis. This is actually the perpendicular axis theorem. So simply this the J is also called IZZ. IZZ, the moment of inertia about the perpendicular axis. If you take the circular member for a circular member, we have in three axes. Axis 1, that is xx. In other axis, this is y-axis, and z-axis is perpendicular to this line. This is actually the z-axis, perpendicular to surface. Then the moment of inertia about the z is equal to moment of inertia about the x-axis plus moment of inertia about the y-axis. So this is came from that one. You know that this is a symmetric about the x-axis and y-axis. Then polar moment of inertia is the value of moment of inertia for the circular section. It's a pi by 64 d power 4 plus. It's a symmetric one. That's why it is common this side and this side. This is a pi by 64 d power 4. If you simplify it, you'll get this value polar moment of inertia. The units may be meter power 4 or power 4. This is about the what you call shear stress distribution, especially they are subjected to torsion. Hello, is it okay? Torsional shear stress and all.
Yes, sir.
Then this is a problem. There is a problem on this torsional shear stresses. The shaft is subjected to shaft of diameter 30 mm and length 200 mm is subjected to axial load of 5 kilonewtons. Axial load means acting along its axis, and the bending load of what you call 7 kilonewtons at its free end. Determine the stresses on the cross section at the given location. So here there are two loads are given. One is an axial load. Axial load is a one load. The value is 5 kilonewtons. Another one is a transverse load, that is a perpendicular load, that is a 7 kilonewtons. And it is also mentioned that that is acting at a free end. So this is an image. So we'd like to calculate the stresses, determine the stresses on the cross section at a given location. Given location means here we have to calculate the stresses at A and B. A and B. For this, I am taking whatever this axis, horizontal axis is X, and axis perpendicular to this member is Y. Then you know that direct stresses can be calculated, or axial shear stresses can be calculated. Normal stresses is equal to induced in cross-sectional area is equal to normal load divided by cross-sectional area. Normal load in which direction it is acting means it is acting along the x direction. That's why it is px here. Px divided by cross section is, it's 30 is a diameter, then pi by 4, pi divided by 4, 30 square is the value. Then if you substitute this is a direct stresses acting on the member. And you know that direct stress distribution is a uniform distribution. Then the distribution is like this, uniformly. What are the 7.07 newtons is acting, Newton per mm square is acting uniformly over its cross section. And it's also called Newton per mm square is also called megapascals. 7.07 megapascals is the stress, direct or normal stresses. Similarly, there is another load which is perpendicular to this member, radial load. So to this, the bending stress is created on this member. The beam will be bent like this due to bending load, and the bending stress will be maximum at this location. To calculate that, we have a formula: bending stresses is equal to m into y divided by I. So here the bending load is 7 kilonewtons, and the bending load 7 kilonewtons is acting at its free end, and thus A is having certain perpendicular distance. The distance is length of the beam L. Then maximum bending moment is equal to load Py, that is acting in the y direction. Py multiplied by the length. Py value is 7 kilonewtons multiplied by length is 200 mm. Then you'll get this is the bending moment maximum. And he asked that calculate the maximum bending stresses or bending stress induced in the member. So for that, we require the distance from the extreme fiber to the neutral axis. Extreme fiber, maybe you may take the A side or B side. A side తీసుకోవచ్చు లేదా B side తీసుకోవచ్చు. Then obviously the geometric center itself is a neutral axis for the symmetric sections. This is actually the symmetric section. So geometric center is a neutral axis. This is actually your y value, maybe this or bottom one also, this is also y only. Then this is your member is a circular member. Your member is a circular member. Then the diameter is already given. It is d is the diameter of this member. Then y value is equal to d by 2. Y or yb, that is equal to d by 2. That is 30 divided by 2. 15 mm is the what you called uh, distance from the neutral axis to hypermass fiber. Then moment of inertia for a circular member about its neutral axis is, we know that it is pi by 4 pi by 64 d power 4. Pi by 64 d power 4. Substitute the d value here 30. If you substitute d value 30, this much is the moment of inertia. And substitute the values here. Bending stress is equal to moment of inertia outward distance divided by I. So moment of inertia calculated, sorry, bending moment is calculated 14 into 10 power 5. and y value is 15. Moment of inertia calculated this, and from this the bending stresses are 528.42 Newton per mm square. And you know that bending stresses are distributed along its cross section. The distribution is flexural. So obviously, the load is acting on topmostly, top to bottom direction. The load is acting top to, downward direction. More precisely, the load is acting downward direction. Then your beam bends due to the downward load like this. Then whatever the layers on the topmost, they will subjected to the tensile stresses. Layers in the bottom of the neutral axis, they are subjected to compressive stresses. So this the value is same because Ya is equal to Yb, because Ya is equal to Yb. Then the stress values are same. So tensile stresses are same and bending stresses also tensile bending stresses on tensile compressive bending compressive stresses, bending tensile stresses, both are same. Okay, this is about how to calculate the stresses when they are subjected to two sort of loads. It is okay up to this? Hello? ఏమ్మా వింటున్నారా? అంటే ఇది యాక్చువల్లీ మీరు ఆల్రెడీ స్ట్రెంత్ ఆఫ్ మెటీరియల్ చదువుకున్నారు. ఒకసారి నేను ఆల్రెడీ రివిజన్ కాబట్టి కొంత ఫాస్ట్ గా చెప్పడం జరిగింది. అంటే తెలిసిన విషయాలే. ఓకే, డైరెక్ట్ ఫార్ములా అండ్ సబ్స్టిట్యూషనే కదా, అవునా? ఫాలో అవ్వగలుగుతున్నారా? ఏమైనా డౌట్స్ ఉన్నాయా ఇందులో? హలో, ఏమ్మా లేవని చెప్తున్నారా, ఉన్నాయని చెప్తున్నారా? అర్థం కాలేదు.
లేదు సార్.
ఓకే, సో ఇట్ ఈస్ 10:33, 10:40 వరకు క్లాస్. ఓకే, shall I move to next topic?
Yes, sir.
నెక్స్ట్ క్లాస్ లో డిస్కస్ చేద్దాం. ఓ పని చేద్దాం, ప్రిన్సిపల్ స్ట్రెసెస్ టాపిక్ స్టార్ట్ చేస్తే ఐ రిక్వైర్డ్ 20 minutes at least to give an clarification. I'll stop here. We'll discuss the principal stresses in the next class. Today we just look on the recollected the what are the simple stresses which the machine member is subjected to. What type of simple stresses? That is the axial loaded stresses, the stresses when the load is axial, and another one is if the load is bending, and if the load is twisting, we are discussing